Now with Professor Frank Lipnizki. He is a professor in chemical engineering with focus on the membrane processes in the Department of Chemical Engineering at Lund University in Poland. Since 2017, he heads the membrane group and manages the membrane lab, the Industrial Membrane Process Research and Development Center at Lund University. Yes, the presentation will be conducted online.
Okay, perfect. Thank you very much for the kind introduction. Yeah, after hearing all these talks about membranes, I would like to talk a little bit about direct membrane filtration. So a new concept for treating actually municipal wastewater. And that's actually a project I'm conducting together with my postdoc, Tobias Hay, who has a lot of experience in this project. So basically, let me start by explaining to you what is actually direct membrane filtration. So basically, the concept of direct membrane filtration relies on the following. The COD fraction in the wastewater consists partly of particular organic matter, which can be easily separated with micro or ultrafiltration. And using ultra and microfiltration or ultrafiltration, we get a retentate, which can be used for the biogas production. And we get a permeate, which can be either directly reused or further upgraded, for example, with activated carbon or forward osmosis. This sounds probably too simple. Therefore, let us have a look at the particle distribution of municipal wastewater. And what we see here is actually that there is a large amount of particles which are greater than 100 micron, and then a smaller fraction which is greater than 0.2 micron. The remains are soluble compounds and water. What we do in our direct membrane filtration process is the following. We take out the particles greater than 100 micron with microsieve, and then we have our micro or ultrafiltration membranes for direct membrane filtration, which are easily taken out in particulates greater than 0.2 micron. The remains in the permeate are soluble compounds and water. So that's the series so far. And we actually jumped quite early on into the cold water by actually moving from the concept to pilot scale. And up till now, we have actually done 3 trials, one in Lund, Sweden. It's the Shelby wastewater treatment plant, which was the initial trial. Then a larger trial in Fredrikstad in Norway at the Flava wastewater treatment plant. And last but not least, the latest trial at the Svedala wastewater treatment plant here in Sweden. That's actually the Shelby wastewater treatment plant. It is designed for 12,000 person equivalent and is the main wastewater treatment plant here in the city of Lund. And basically, we installed the pilot where you can see the red rectangle. So it was directly integrated into the wastewater treatment plant. So this is actually the pilot. What you can see is actually here the container, and it was located basically after the center of the wastewater treatment plant. Then we had actually a coagulation, flocculation step, microsieving, and microfiltration. A little bit more detail. So here you can actually see the 2 steer tanks for the coagulation and flocculation part before the microsieving. Here you can see the microsieves, how they look like, and you can see also they have a 100 micron filter cloth. And then we find, last but not least, we have the direct membrane filtration unit. Basically, these are submerged membranes supplied by Alfa Laval with a pore size of 0.2 micron. It's basically their standard membranes they're using or used at that stage in time for the MBR module. And we use this module submerged in a tank for our direct membrane filtration. The membrane area was just 1 square meter, but that was actually sufficient to get an initial feeling. We will also look a little bit on different types of setups. So the screen, a sand trap was always used as a pre-treatment. And we also decided early on, after doing some initial thinking and testing, that actually a microsieve has to be in front of the microfiltration unit. So we never really tested on large scale the direct use of microfiltration because we believed it was not possible. However, what we spent a lot of time in was to look at other pre-treatment steps. The coagulation step, microsieving, coagulation, flocculation, microsieving, and flocculation alone with microsieving. And there we looked at the different results we achieved. And what one can nicely see is actually basically with even already with mechanical separation, so with the microsieve, we achieved quite good values for the BOD, but also with the other technologies. The total phosphor was not sufficient with the microsieves. The fluxes, what we could see is actually we achieved very good fluxes with coagulation, and we also with coagulation plus an anionic polymer. So that was quite encouraging. Nitrogen, we also removed quite nicely. But the best way we tried to move forward was actually coagulation with an anionic polymer, which gives us nice fluxes and a very good removal. And basically, when it comes to discharge limits for wastewater treatment plants for less than 10,000 people equivalent, then we were fine in these requirements. And often pictures say more than 1,000 words. So here you can see actually the water going into the direct membrane filtration unit and the crystal clear water which goes out of the unit. Encouraged by this result, we went to Norway, to the Frava wastewater treatment plant. It's in Fredrikstad, which is not so far away actually from the Swedish borderline. And there we have also a wastewater treatment plant with actually an anaerobic digestion and co-digestion. What we installed here basically was a concept which we found out was the best concept from Lund. So we take the wastewater in, the municipal one, screen it, sand trap, coagulation, flocculation, microsieve, and then microfiltration. So here you can see actually the larger plant, how it looks like. So the sand trap, the coagulation, flocculation, the drum filter. And we basically went from 1 square meter from the previous plant, we went up to 386 square meters with membrane areas. And we achieved actually quite decent fluxes. That gives us, the plant was giving us a flux of 10 liters per square meters per hour, which resulted in a total capacity of the plant of 92 cubic meters per day. Also some results, COD was less than 100 milligrams. The total phosphor was less than 0.5 milligrams per liter. Flux, as I mentioned before, 10 liters per square meters per hour. And we had a transmembrane pressure of minus 0.3 bar. And that was quite okay with the Norwegian discharge limit. Again, you can see nicely the results that the water which was in front of the direct membrane filter and the water after the filter. Then actually with this concept, we joined a European project, Less is More. And this project was focusing on the increasing use of pharmaceutical and other types of organic compounds with different types of biological effects. And actually, our wastewater treatment plants, say in Scandinavia, are not really suited to handle this type of component. And when they are discharged to the environment, they might have a negative impact on the aquarius system. So, and when we could remove them, I mean, we are very close actually to drinking water. Maybe there could be even a possible recycle. So how handle this component? Basically, again, we took the same concept, screening, sand trap. Then we had coagulation, flocculation, microsieve. But then comes the first big change is actually we tested microfiltration, ultrafiltration membranes in parallel. And as a post-treatment, we added granulated activated carbon. And this is actually the pilot we built up at the wastewater treatment plant in Svedala. So the first step, coagulation, flocculation. And here we had a wastewater flow of 3 cubic meters per hour. We use PXXL60 as a coagulant and dosing 300 milliliters of aluminum per hour to the tank. And we do use a 150 anionic polymer, 3 milligrams per liter, dosing at 9 liters per hour to the tank. Then we had the drum filter. And I mean, the main change here is actually we went for a larger filter, but it was still a 100 micron sieve, and we had a 600 liters intermediate tank there. Then came the microfiltration and ultrafiltration part. And here we tested actually 2 different types of membrane. We tested the microfiltration membrane 0.2 micron, which we used successfully in the previous trials. under the motto, never change a winning team. But we also tested an ultrafiltration membrane with less than 0.01 micron. It was actually a 10 kilodalton membrane. And then last but not least, we had granulated activated carbon as a final polishing step. And we had 3 columns granulated activated carbon for testing the wastewater treatment plant effluent directly, so the original effluent, which came after the processing of the water out there, the microfiltration permeate, and the ultrafiltration permeate. And the empty bed contact time in all 3 cases was 15 minutes. And here you can see what we really achieved when it comes basically to the organic dissolved organic matter and the organic matter reduction. And what you can see nicely in both cases, I mean, really, we achieved a very nice reduction with our setup using the ultrafiltration, both DOC and also organic matters were actually reduced significantly. Basically on the same level or better than the standard wastewater treatment plant. We have to keep in mind the standard wastewater treatment plant is quite large, and this is really a very, very nice compact solution. And also when it comes to the reduction, for example, of some pharmaceuticals and herbicides, for example, here we have TreatmentProf, which is a widely used herbicide. We can see actually that the ultrafiltration is effluent, and also the standard effluent after treatment with activated carbon is actually perfect and much better than it was before. With this, I come to my conclusion and outlook. I mean, what we see is actually the direct membrane filtration concept matches the discharge limits for small and medium-sized wastewater treatment plants in Scandinavia. That means especially Sweden and Norway, where we did the trials. Most carbon is retained, I mean, as sludge and retentate, and you can use it then for biogas production. That means actually the whole process, if it's designed properly, is energy neutral or a positive energy wastewater treatment process. So that's something I think is quite excellent about this process. Furthermore, when you compare actually the footprint of the direct membrane filtration plant compared to a conventional wastewater treatment plant, it is significantly smaller. And also the number of pre-treatment steps are reduced. And our ongoing research focuses now on the reduction of micropollutants. For example, also what is actually the fate of microplastics in the direct membrane filtration permeate when you, for example, use activated carbon as the final step. And with this, I would like to thank my co-workers, Tobias, Federico, and Simon. And I hope this whole concept will contribute to the global sustainability goal number 6, clean water and sanitation. Thank you very much, and I'm looking forward to your questions.
Thank you very much for the interesting presentation. Now with questions from audience.
Very nice talk, Professor Frank. How about the cost-performance ratio of this your study? The cost-performance ratio, very interesting work you have done, Professor Frank.
I think it's actually, we did a comparison study, and I mean, it's also from the cost comparison. It is actually an interesting process, and one of the key factors is really it needs so much less land. And certainly, I mean, land is actually a significant value, especially when you have wastewater treatment plants in urban areas where when you can actually sell or reduce the land used for the wastewater treatment plant is a key factor. And the other thing is actually it becomes energy neutral. So I think from both the OPEX and CAPEX, this is a very, very interesting concept to follow on.
Right. Did you use any commercial membranes or polymer-based membranes?
The membranes we are used were always basically commercial membranes from Alfa Laval. The only thing where Alfa Laval helped us was actually they helped us with putting these membranes on their module. So basically the 10 kilodalton membrane was a special membrane done for a special module done for us. Otherwise, everything was commercial.
Thank you. Any other question from the audience? Okay, Professor Frank, thank you very much for this interesting presentation.
Thank you.